All right, so on Wednesday we talked about two different kinds of curves. We talked about banked curves and unbanked curves, right? We also talked about centripetal force in general, right? When we are solving a centripetal force problem, okay, the things we have to remember are that centripetal force is really net force, right? And the way we calculated net force in the last unit was, okay, so we could do mass times acceleration, which for a circular moving object is mv squared over r, okay? And what was the other way? What was the other way to calculate net force? The sum of all forces. All right. So we said in that one, okay, sum of all forces. Well, it's also true for an object moving in a circle. We just have to figure out what force is providing the centripetal force. Okay. Centripetal force is not a force that's separate. It's a force that's being provided by some other force, in the same way that net force is the sum of all the forces that are working together, right? So the trick with circular motion is identifying what force is acting as the centripetal force. For an object going around an unbanked corner, what force acts as the centripetal force? Friction. Okay? Friction keeps you from sliding out of the corner, right? So in the case of this question, Fc is equal to the force of friction, or Fc is being provided by the force of friction. I'm going to give you a few minutes to copy that question down. This should give you a start on it. See if you can solve for how fast this car can go around this corner, being held only there by friction. Okay, so I'll give you a few minutes to see if you remember how to do that. All right, so our givens for this question are that the mass of the car is 1,500 kilograms, although we'll find in a minute that that won't matter. Okay, it's rounding a curve that has a radius of 40 meters and a coefficient of static friction, okay, that is 0.60. All right, friction is providing. Friction is providing our centripetal force. So that means, just like in the last unit, I set m times a equal to the formula for the force of friction. Okay, so that's going to mean mv squared over r equals mu times the normal force. Okay, now, because this is not, or because this is an unbanked corner, that means it's level. On any level surface, normal force and gravity are equal. Okay, so that means then that I can take Fn out of here. How do I usually calculate force of gravity? Mass times gravity. That's why I was saying the mass isn't going to matter, because once I start manipulating this, mass is going to cancel. All right, so I'm manipulating here to find V. So I'm going to move r over first by multiplying both sides by r. I'm going to divide both sides by m. Okay, and that's going to leave me v squared equals mu times g times r. I want v, not v squared, so I'll be left with v equals the square root of mu. Okay, I spoke that before. Now if I plug in my numbers, okay, v will equal the square root of 0.6 times 9.81 times the radius, which is 40 meters. Square root of 0.6 times 9.81 times 40. Okay, so we got 15.3 meters per second. Actually, we only have two significant figures here, so this is going to be 15 meters per second. Okay, that is the speed at which the car can round the corner. Everybody all right with that? Yes. Okay, let's have you guys try these ones. Okay, we'll skip number one because we just did one that's exactly like that, so we'll skip that one. Okay. Even though this is like the first time that I put that question up, and the Oilers are actually leading their division. True story. It's been that long. Okay. As an Oilers fan, that's hard to take, but it's nice that it's actually happening. Okay, so try 2 and 3. Okay. All right, so for number 2, okay, we're told that we're using a large circle with a radius of 100 meters. Okay, we're told that it increases speed until it gets to 95 kilometers per hour, which we have to convert right away into meters per second. Okay, so we'll have 95 divided by 3.6. Okay, so 26.38. Repeating, okay, meters per second, and we're told the mass of the car, which is going to cancel anyway, it's 1,200 kilograms. Okay, since this is an unbanked corner, we know that Fc equals the force of friction. That's mv squared over r equals mu times m times g, because again, gravity and normal force are going to be equal in this situation. All right, so we are looking for the coefficient of friction between the tires and the road. So we're going to divide both sides by m times g. Okay, so g comes over, m is going to cancel. Now, here's something I want you to look at. In an unbanked curve, friction is what provides the centripetal force. The other day we also learned about banked curves. And the formula for a banked curve was that the tan of theta equaled v squared over r times g. What do you notice here? Yeah, it's the same formula. Okay, because these are both circles. It's just a different thing that's holding it in a circle. For an unbanked circle, okay, friction holds it in. For a banked circle, the angle of bank is what holds it in. Okay, that's why the formula comes out to basically the same thing. Okay, we're just solving for something else. Instead of friction, we're solving for the angle of bank. All right, so back to this question here. Okay, I just have to plug in my numbers, so that'll be 26.38 repeating squared divided by 100 times 9.81. Okay, so squared divided by 981. All right, so we're looking at a coefficient of friction of 0.710 because we have 3 significant figures here. Okay, everybody all right with that? Okay, how many people have done number 3? How many people need a minute or 2? Or okay, I'll give you a minute or 2. 3. Okay, so on number 3, we have a 600 gram. What do we need to convert that to? Kilograms. Not going to work in grams. Okay, so our mass is 0.6 kilograms. Okay, and it's going to make a turn at a speed of 3 meters per second. Okay, and the coefficient of friction is 0.9. All right, so again, it's an unbanked corner, so Fc equals the force of friction. mv squared over r equals mu times m times g, so that mass that we converted won't even matter anyway. We're looking for the radius of the turn, so I'm going to multiply both sides by r, so it's on the top, and I can solve for it, and then divide both sides by mu times g. Okay, so that'll solve for r. So r will equal 3 squared, that's with the speed, divided by 0.9 times 9.8. That should give us 1.0. Okay, questions on number 3. Okay, so I'm going to have you work on some centripetal force questions from the digital workbook here. They're not all going to be unbanked corners, okay? There's going to be different types of situations in there. So you're going to be determining what force is acting as a centripetal force, okay, in those situations there. Okay, so it's in Google Classroom, guys. If you bring that up, it's in the class work section. I'm just bringing up my copy here. Okay, and we are going to be looking at, okay, this first or second page. So page 2, right? We're looking for, okay, answering these questions here. Some of them are really simple. They're just mv squared over r. Okay, and then other ones are going to be like the banked curves, the unbanked curves, okay, and things like that. Right? So I want you working on those. Okay, for right now, if there's any that give us trouble, then we can go over them together. So, most common mistake with number 2 is not going far enough. Okay? You're being asked to calculate the centripetal acceleration, AC. Okay? Not V. You're being asked to calculate the centripetal acceleration, which is V squared over R. Now, you're not given V, but you're given the period, which needs to be in seconds. That's the second most common mistake. Okay, it needs to be in seconds, right? And we need to calculate that. Now, what some people do is they go, okay, V equals 2 pi r over t. They solve for that. Then they plug V in. They plug that in for V. And that's fine. But in this unit, we're going to have to do something called substitution on a fairly regular basis. What substitution is taking a formula and plugging it into another formula, okay, for this variable. So V is in here, right? But in this formula, V is squared. How do I square this formula? You just square everything. Yeah, it's actually that simple. What's 2 squared? 4. Okay, what's pi squared? Pi squared. It's a trick question. Okay, what's r squared? R squared. Okay, and t squared is t squared. That's pretty easy, right? Okay, now I take this and I simply plug it in for V. So I'm going to take the V out, and I'm going to plug this in where V was. Now I've got my formula.
Wouldn't it just be the same if you calculated?
It would be, but here's the thing. There's going to be some situations later in the unit where I don't give you enough information, like, or I ask you to calculate period, and you have to substitute in and solve it in this formula instead of this one because I don't give you R or something like that. So being able to substitute is an important skill that we have to have in this unit. Right? So now that I have that, now I can solve for A without having B. Okay? So I'm going to go 4 pi squared times 3,282 squared. Okay? Actually not squared because I've got an R on the top and okay, so the squared cancels. This R goes away. Right, so I'm just going to have 3,282 over 120 squared. Okay, why is it 120? Because it needs to be in seconds. Okay, so when I do that, okay, I'm going to have 4, and then just use the pi button, squared, okay, times 3,282 divided by 120 squared. All right. 8.9977, so that's 9.0 meters per second squared. Yeah. All right, yes. All right, keep going there, guys. Are there any other ones giving us trouble? Okay, keep going then. I'll put them back up on the board.